Okay, we can start. Welcome everyone to the DGRAV seminar. Before we start, I would like to remind everyone of the APS code of conduct to have a healthy and friendly environment. And I would like to remind you also to join DGRAV if you haven't yet. And on screen, you can see two codes which allow you to nominate speakers and access previous recordings. The format of the seminar consists of three parts: a short, broader overview, followed by a longer technical presentation. Any question besides short clarifications should be held for the third part, that is a discussion session with both speakers. And today we are very lucky to have Gabriela González and Debasmita Nandi from Louisiana State University. And they will tell us about noise sources in the LIGO for observing run.
Thank you, Genio, and thank you, Deborah, for inviting me to give this on short notice, but I'm very happy to do so. And this is not the general talk I usually give. There are much better experts on noise sources than I am, but I'm very glad to tell you about this and remind you about the noise in LIGO. It used to be everything we talked about was noise. Now we have lots of signals to talk about, but noise is still there. Okay, so you might remember that this year we celebrated the 10-year anniversary of the first gravitational wave detection, and we have here the signal that was saw with a peak amplitude of 10 to the minus 21, and you can see the noise that we had in there. This was the signal from the merger of two black holes of about 37 masses each. And one of the ways I like to show the improvement, and this, I haven't given credit here, but this graphic is credited to Greg Davis, is seeing a very similar signal, very similar amplitude, very similar black hole value system, but in January of 2025, a bit less than 10 years later, and you can see how much smaller. But we have improved things a lot. And I wanted to give a bit of a historical perspective on this. So I'm going to start reminding you about LIGO. I know that most of you probably know this by heart, but LIGO consists of two observatories in Hanford, Washington, and Livingston, Louisiana, 4 kilometers baseline. And we are measuring amplitudes of about 10 to the minus 21 and smaller now, which requires measuring displacements, differences in distance, and in a certain frequency band, less than a proton, less than 10,000 of a proton, now less than 10,000. But again, I want to give you a historical perspective. This project, the first signal we had was in 2015, but that was a long time after the effort began. This was one of the first papers on LIGO in Science presenting the LIGO project. And I'll show you a figure from there that have the estimated noise that these detectors would have, not just 3 detectors, they would be 2 in Hanford, 1 in Washington, but also future detectors. Even from the beginning, there was the idea of first generation, now initial LIGO, and its second generation, called now again advanced LIGO. Sometimes it was called LIGO 2. And that was a sensitivity that was expected to be limited by very fundamental sources in the ground, even isolated seismic isolation, pendulums, and seismic isolation, the Brownian motion, and the quantum noise. We have learned a lot more since then about predictions of certain noise. This prediction is not right. It's actually more like this, and this is quantum noise, which is much better understood. So, initial LIGO operated between 2000 and 2010, And it achieved its design sensitivity. This is the noise, the measured noise as a function of frequency. This is the amplitude spectral density in strength. You can see that it is what was promised. The dash behind was what was promised in the 2 4-kilometer detectors. The blue line was the 2-kilometer detector that people sometimes don't remember. We had a third detector, H2. 2 kilometers, and it was half as sensitive because it was 2 kilometers. It took several years to achieve that sensitivity, and we learned a lot about what were the dominant noises in here. Fast forward to 2015, we actually were in the beginning, about to start the first observing round of advanced detectors. We were not at the sensitivity. We are never at the sensitivity we always want to do better. But we were far from what we call design sensitivity, and this signal surprised us all. And it was a very, very good surprise. And you know that we have had many, many such surprises since then. Well, not so many surprises now. Now they are expected. Now, the sensitivity that we had here in 2015, that was in the very initial era of advanced LIGO, it's here. This is the amplitude spectral density in meters. So if you want it in strain, you have to divide by 4 kilometers. But when you want to relate these to ground motion and other things, sometimes we use it in meters. And you can see here that we were limited by quantum noise, short noise, phase noise, and frequencies. We were limited by seismic noise, but there are many, many other auxiliary technical noises, as we call them. Seismic noise was much, much below. We had a lot of work to do to get from here to here. Here you have the strain noise, and this is the best we had in the initial LIGO era. In 2010, 2005 or 2010, we did better than the design sensitivity of LIGO. This is what we have, and this is where we wanted to go. This was the design sensitivity. So quite a bit to get, and that's what noise is about. As you probably know, we took data for about 3 months in 2015, 2016. We had 3 detections then. We took data for 6 months in 2 in 2016, 17. We had the spectacular neutron star merger, like 7 black holes. We had a third observing run, more detections. Sadly, only 1 had a neutron star merger. We started taking data testing, taking data with DGRAV. We had a long break, in part due to COVID, in part due to upgrades, and we took data in 04, which we just finished taking data a couple of weeks ago. Now, again, going back to the noise, from 2015, when we had the first observing run to the second observing run, we reduced the noise a lot at low frequencies. This is LIGO Livingstone, and you can see here. And when I say we, I didn't do anything. When I say we, I refer to the people on site, scientists on site, graduate students, fellows on site. So this is the sensitivity, the noise we had in 01, and you can see how much smaller we got it in 02. And that was mostly due to really going after many of the control loops, the noise introduced by the control loops. From 02 to 03, so that's from gray to blue, there was a huge improvement in the high frequency band. And that was due to the use of higher power, more photons, less noise, but also vacuum squeezing. In 03, that was not in the baseline of advanced LIGO, but it was a technology that was ready to be installed. It had been tested at the end of initial LIGO, so it was installed because increasing the power has turned out to be a lot more difficult than thought in the beginning, and squeezing is right there. So we got to 130 millipads. The advanced LIGO design sensitivity was around 170 megaparsecs. We still had a bit to go, and we did from 03 to 04, where we use here, we couldn't use more power or more squeezing because that was going to introduce more noise from radiation pressure at low frequencies. But in 04, we had what we call frequency-dependent vacuum squeezing, which means that we don't introduce just a squeezed vacuum in here, in which we can only choose whether to squeeze phase noise or amplitude noise, but we make the squeezed vacuum go through a cavity, and that's not any cavity, it's a 300-meter cavity, so it's not 4 kilometers, but it's a macroscopic cavity. We needed new installations. And then that squeezed vacuum in here now is squeezed in phase at high frequencies and squeezed in amplitude at low frequencies. So that's how we can use still a bit more. Go to 175 megaparsecs, but cheating a bit because this was not in the baseline that we had. So this has gone very, very well. There are still more ideas, still more ideas on how to improve things further, especially doing more squeezing, more increasing the power and reducing this multitude of noise sources at low frequencies. Again, this is not what I'm going to talk about, but you know that with this sensitivity and this science run, we have had a multitude of signals. We just published the catalog that has 218 signals from 01 to 04. To the first part of 04, we still have, that is this first part of 04, we still have 04B to analyze and 04C to analyze. So there's still more signals to come, but we already have more than 200, and if you count public alerts, more than 200. Sadly, we still only have 2 neutron star mergers. We have a few more neutron star black hole mergers, but that's so many black holes. Some there have been some articles calling like the black hole machine. As I was telling you, if you look at the low latency detections, there are already, well, there were, because we stopped taking data, 254, plus the ones we had published in 0103, so there's quite a bit. And even there's a strange signal in here that doesn't say binary black hole or an SVH. It doesn't have any label, because it was detected by a certain algorithm that was searching for binary systems with masses less than 1 solar mass. Less than 1 solar mass. We call that sub-solar mass. However, what we publish with all of these detections is a false alarm rate. How often can a signal like this be produced from just noise? Not Gaussian noise, but the realistic noise that we have in the detector. And here you can see that this is, we would have to wait 5 million years to get a signal like this just from the noise. But for this one, it's 6 years. It's not so long. So we still don't know. This is not a groundbreaking discovery, at least not yet, but it's a new thing. Now, this false alarm rate, where does it come from? Well, that comes from the noise I was showing you before in the spectral densities. This is produced for the most part, the spectral density noise is produced for the most part by Gaussian noise. It's very stationary because it changes a little bit during the day and night, summer and winter, but it's mostly stochastic. But on top of that, we have many, many transients, and those transients look like signals, especially if you're looking for unmodeled signals. This is one of the last papers that has been posted. It's been under review for the search of gravitational wave transients. So these are unmodeled transients compared to the false, the inverse false alarm rate years. So these are real signals, because the inverse false alarm rate, if you extrapolate this curve, is millions of years, or thousands of years. So these are very clear signals. However, all of these are also found by the algorithms that look for binary mergers using the waveforms of binary mergers. So we know that those are binary black holes. And if you exclude those, then you have this. So we have not detected any transient that is not the merger of a binary black hole system. But we would like to. So what we would like is for this to be a lot smaller. This is a lot larger than what you expect from Gaussian noise. And why is it larger? Because we have a lot of glitches. And characterizing the detectors, not just these transients, but the periodic, continuous periodic noise, the stochastic noise, characterizing the detector is something that a lot of people in the LIGO collaboration do. This is a recent paper. I see that I will add the reference here. I see that the reference is new, but this is in classical quantum gravity. A paper led by Sid Soni, also a young early career person, but a lot of other people, Debasmita among them. And these are spectrograms that from those glitches. These are extremely loud glitches, lots of yellow there. There are some others that are not so strong. There are some that look like arches. These are the ones that Smith is going to talk about later. And if you look at how often this happens, we have plots that we produce every day. This is from the same paper. And every dot in here, these are 24 hours. Every dot in here is a glitch. Every dot. And there are thousands and thousands of dots. The color represents the amplitude of the signal to noise ratio, so most of those are not loud. But they're still for the background. They still limit our astrophysical sensitivity. And you can see lots of blue dots. Most of those are these loud triggers, but you can also see some that accumulate along some frequencies. Again, this is frequency, this is time. So these are what we call 20 hertz glitches. These are 10 hertz glitches. And it's detective work that we have to do to find out what are these glitches, where they come from. We give them names, but that doesn't help to eliminate them. There is a very famous glitch that you might remember that was actually for the binary neutron star signal. In the Hanford detector, there was a clear signal. In Virgo detector, there was not a signal, but we knew that Virgo could see signals because we had seen a binary black hole merger just a couple of days before this one. So the fact that it was not there meant that it was along the null direction. So that was very good. But in Livingston, we only had this very pretty clear signal after we subtracted this huge glitch that actually almost fooled the early alert. It fooled the early alert system that we had, and it was humans paying attention, the ones that allowed this early alert to go out and alert the astronomers and get all the astronomy we had from that time. So these are important things to take care of. I was telling you about the weights. Well, if you look at the not so loud glitches, like a signal to noise ratio larger than 6.6, 6 is loud for gravitational waves. These are glitches. We see that this was in Hanford, this was in Livingston during first part of 04, and you can see that there are bad times, but there are almost no good times. If you look at louder glitches in 04, then it was a lot quieter. At Livingston, it was a different story. It was quieter in the beginning, and it was more noisy during the end. This is winter. It was a lot noisy in winter, and that's because there was a lot of these was due, even loud ones, were due to scattered noise, which is one of the worst sources of noise that we have. It produces most of the glitches that we see. These are loud glitches. And those are the ones that Debasmita is going to talk about. So this work is important, even though we stopped taking data now in 04. It's probably going to be at least a year. We are thinking about taking data again late next year. But it's important that we know where the sources of noise were in this run so we can avoid them in the next run. So the work is not done. Even though the data is taken, we are still doing that detective work to see where those glitches came from so we can avoid them in the intermediate runs intermediate data we may take. And hopefully, depending on funding and the national landscape, the national funding landscape, we hope to be achieving the sensitivity that we can aspire with the upgrades that we are doing. Frequency dependent squeezing, hopefully having masses with less thermal noise, and suppressing, being able to use even higher power. So that's what we are doing now. And that's what this is what I would like to end to show you 10 years progress in noise, in stochastic noise, but a lot of work is needed for the transient noise that Debasmita will be talking about. So that's my introduction. Noise is important even now.
Thank you, Gabriela. Debasmita, please go ahead.
Okay, I will share my screen. Is my screen visible?
Yes, it looks good.
Okay. So as Gabby mentioned, I am going to talk about this particular population of glitches which is caused by scattered light, and especially at the LIGO Livingston detector in O4. And we had seen glitches caused by scattered light in the third observation run as well. And the sources of those glitches were found and mitigated. But this is some other source that is creating the noise in the fourth observation run. To begin with, I will go over the brief introduction about scattered light noise. This figure here shows a simplified schematic of how this noise couples into the detected data. So because of some inbuilt imperfection, all the mirrors scatter a certain fraction of the light incident on it. And if that scattered beam hits another moving surface in the vicinity, and it gets reflected back from this moving surface and joins the main beam, then because of the motion of this surface, this scattered beam has a different phase than the main beam, and the phase also changes because this surface is moving. And our goal is to find these scattering surfaces which are creating the noise. So here is a brief math. So we assume that these surfaces have a sinusoidal motion at a particular frequency, and then we can calculate the phase difference caused by this variation of motion, and that phase difference translates into the strain data by this formula. Here A is the amplitude of light that is there in the scattered beam. We usually represent this as a fraction of the main beam, and lambda represents the wavelength of the laser that we use inside LIGO, and this is 1064 nanometer for us. L is the 4 kilometer long arm of the detector, and this is the noise in time domain. If we take a Fourier transform of that, we can get the noise in the frequency domain as well. And this spectrogram here shows a representation of these glitches in the frequency versus time spectrogram. In the y-axis here, it is the frequency is shown, and the x-axis shows the time, and this is 15 seconds long spectrogram. And this glitches caused by scattered light has this very characteristic morphology of arches. They always appear as repeating arches in the detected data. If we look at the noise spectra of the detector, this is how these glitches affect the astrophysical sensitivity of the detector. They typically affect us in between 10 to 40 hertz, and the noise created by these glitches appear as this shelf that is shown here in this red trace. There is a certain horizontal component of for a certain frequency. This will be kind of flat, and then it drops down, and we can extract some information from this characteristic shape of the noise. We need to know where three important parameters which we need to characterize this noise, and those are the velocity of the scattering surface here, and the frequency with which the surface is moving, and the light amplitude that is there in the scattered beam. And I will go over each of them in the later slides. So here is the scattering in O4. This is the Omicron diagram that Gabby showed before, and this is from a day when we had a lot of glitches caused by scattered light. If you look at the population of the glitches, we can clearly see there is two different populations. One which have this very high SNR. These are the high SNR glitches that appear in between 10 to 40 Hz frequency bands, and these are the worst for the astrophysical sensitivity because they have loud SNR. They affect us more. And then there is another group of glitches which appear around 20 Hz band. They have this pretty consistent frequency around 20 Hz, and they have slightly low SNR if compared to these high SNR glitches. These are the main two groups of glitches that we identified in O4 that affects the low frequency sensitivity. So first I will talk about these high SNR glitches. Here is a plot of the hourly glitch rate of the high SNR glitches as a function of ground motion. The red trace here shows the hourly glitch rate of these glitches, and in orange and green we are showing the ground motion in two different frequency bands. The orange is a zero point 0.1 to zero point 0.3 Hz frequency band ground motion, and the green is 0.3 to 1 Hz. So these are ground motion at very low frequencies below 1 Hz, and they appear mostly because of the ocean activities. And since Livingston is so close to the Gulf of Mexico, we get more affected by this microseismic ground motion than Hanford. And from this plot we can see that both these bands of motion are creating these glitches because there are certain peaks in the glitch rate which is pretty closely aligning with the high amount of ground motion in 0.3 to 1 hertz band. But there are also some peaks which are at the same time when there was a peak in the zero point 0.1 to zero point 0.3 hertz ground motion. So we know that all of these motions below 1 hertz are affecting these glitches. Now I will talk about the three important parameters that I told before that we need to know to characterize this noise. The first one is the velocity of the scattering surface, and we can guess the velocity. We can give a rough estimate from these spectrograms because this noise appear as these arches. If we look at the peak frequency of the arches here from the y-axis, we can tell the velocity of the surface from this formula. And stacked arches mean there are multiple reflections of the same scattered beam, which is denoted by n here, and VSC is the velocity of the scattering surface. So if we as we can see that all these arches have a peak frequency around 20 hertz, that means that we need to have at least a 10 micrometer per second velocity to create this noise. But this is a lot of motion, and we have checked and verified that none of the mirrors inside the detector have this much motion. So only possible ways to get this much motion is from the ground, if the scattering surface is directly being modulated by the ground motion. Now the second parameter is the frequency of motion, which is a very important clue that we get about the scattering surface. And we can tell the frequency of motion from the separation of these arches, the time separation between these consecutive arches. And three peaks of the arches, three consecutive peaks means one cycle of motion. And we can see that in the top panel here, one cycle of motion takes around 6.5 seconds. So this if we take the reciprocal of that duration, we get 0.15 hertz, which means that on this day this scattered light noise was created by a 0.15 hertz motion. Then there is some other day when we see that the scattering surface has a frequency of motion which is close to 0.3 hertz or 0.4 hertz, which tells us that the scattering surface does not have a specific frequency with which it moves, which is very different than what we saw before, because in O3 when we had these glitches created by scattered light, the scattering surface always had a characteristic frequency which corresponds to the resonance frequency of that surface. But since we don't see that in O4, we know that this surface does not have a very specific sharp resonance at a certain frequency. Instead, it is a low Q resonance surface which does not have a very sharp resonance. The third parameter that we need to know is the light amplitude, and the way we calculate this is by fitting the noise spectra using this formula, and we fit this formula here. This is shown in the orange trace here, and we have seen in different examples that we need a light amplitude of 2 to 4 times 10 to the power minus 10. This is a fraction of the main beam in amplitude. If we translate it into power, it needs almost around 10 to the power minus 4 watt in power, and this much amount of light is very high, and it is unusual to get this much light from anywhere except the main beam that is inside the 4 kilometer long arm cavities. Now I will talk about the modeling that we have developed two models to explain this noise. Uh, but before going into the models, I would like to briefly explain the suspension and seismic isolation system. So this is the figure that I took from the suspension paper. The blue pillars that you see here, these are the HEPI system. This is the first stage of seismic isolation that isolates the mirror from the ground motion. And all the test mass mirrors are mm, uh, suspended from seismic isolation platforms which are attached to this HEPI. So you can see here two stages of seismic isolation. We call these stages ISI or internal seismic isolation. And from the second stage of ISI, the test mass mirror hangs as a quadruple pendulum. And we also have some structures like baffles, which hangs from this HEPI, and they are just in front of the test mass mirror. These help to block some of the scattered light that is being scattered from these mirrors. And in the past, we had issues with these arm cavity baffles. They created some scattered light noise. So initially, we suspected them. So one of the models that we developed is to explain if there is any scattering going on between the test mass mirror and these baffles. But there is a trick here that these baffles do not have any motion sensor attached to them, so we cannot directly read how much they are moving. We need to use some other sensors, and then we model the motion of these baffles. And the second method that we used was to explain the scattering if the scattered beam is directly hitting the chamber wall from the test mass mirror. So these are the two different ways of modeling that we did. Uh, this is a brief motivation behind the first model, where we modeled the baffles and the motion of those kind of structures, uh, where we have seen that this is a noise created by scattered light in DARM, and this glitch was created by a 0.17 hertz motion, because the separation is close to 6 hertz. So it's around 0.17 hertz motion. And we have seen that on for this particular example, if we amplify the ground motion by a factor of 2, we can create the same arches at the same time as seen in DARM. But then for another day where the scattering was due to a 0.4 hertz motion, we have noticed that we need a higher amplification factor to match the level of noise. So for this day, we had to amplify the ground motion by a factor of 6. This tells us that the scattering surface might be amplifying the ground motion more at these frequencies, which is close to 0.4 hertz, 0.3 hertz, than it is doing at 0.2 hertz. So, after seeing these examples at different instances, we decided to model the transfer function of the scattering surface And this is the model that we used for the transfer function of the scattering surface. We modeled it as a damp driven harmonic oscillator having resonance at 0.45 hertz, and we used a low quality factor of 20. And for this, we use the motion of the happy platform, since these buffers are suspended from that platform, and amplified motion of that platform by this transfer function. This is an example of what we get from our simulation. The top panel here shows the actual noise in down, and the bottom panel here shows what we get from our simulation. This the rightmost plot here shows the noise spectra as a function of frequency. The orange trace shows a background spectra when we don't have any noise, and the blue trace here is the noise spectra created by this glitch, and the green trace shows the fitting that we get from our model. Then this is the second way of modeling the noise, where we assume that the scattered beam is directly hitting the chamber wall, not anything suspended from that. So for that, we don't need the pendulum transfer function that we were doing in the previous model. Here is an example of what we get if we assume that the scattering surface is the chamber wall itself. The bottom spectrogram shows the simulated noise, and here in the right side in this plot we are showing the shelf created by this. As before, the blue trace here shows the noise uh, created by this glitch, and the green is the fitting from our model. So after doing the modeling, we did the correlation analysis to localize the source of the noise. For that, we calculated the Pearson correlation coefficients between the RMS of motion in between 0.05 to 30 Hz and the RMS of the gravitational wave channel, which we call DAN. And for that, we use 15 to 40 Hz because these are the frequency range where these glitches appear. And we used sensors located at different chambers, which measured motion along different direction. The so BS means beam splitter, ITMX means the input test mass mirror, ETMX means ETMX, and ETMY means the end test mass mirrors along the X and Y arm, and the subscripts here denotes the angle direction of motion. And we repeated these calculations for a lot of glitches. For this table here, this is a result of analyzing 600 glitches, and we note down the average correlation coefficients here, and from both the models we get the highest correlation from the corner station when we use the sensor that is measuring the motion along x direction. So this tells us that the corner station ground motion along the x direction is the one which is the most correlated with the noise. Now I will talk about some instrumental upgrades that have been performed during the last vent period. So from April to July, the detector was down for maintenance, and then people have installed these structures inside next to the test mass mirrors, which we call the cage buffers because they are attached to the suspension cage. This helps to block some light which is scattered uh, through the side of the test mass mirrors, and this is the face of the test mass mirror. And after installing the cage buffers, we have seen a significant reduction in the glitch rate. Here is the same plot that I showed in the beginning, which shows the glitch rate as a function of ground motion. This is what we had in the last winter, and this is what we have now. And as you can see, given the same amount of ground motion, the glitch rate is much lower now than what it was before. Not only the glitch rate has gone down, but also we have seen that for the existing glitches, we still have a few of them left, but their amplitude is less now. This plot here shows that reduction in the amplitude of glitches. Here I am plotting the amplitude of the glitches on top of the characteristics trend. The red dots here show the glitches that we had in the last year, and these blue dots here show the amplitude of the glitches now. And it is showing a good amount of reduction in the glitch amplitude. that means the signal to noise ratio of these glitches will also be less. And this plot in the bottom right shows the astrophysical sensitivity plot. The red trace here shows how much these glitches used to affect us before, and the blue trace is showing how much it is affecting the sensitivity now. And we can see this improvement of almost a factor of 5 to 6. Now I will talk about the low SNR glitches. This is the other group of glitches that we have noticed appearing in the detector. Most of the days when the high SNR glitches are there, we cannot see them very clearly because they hide behind those high SNR glitches. But there are only a very few days when we don't have the high SNR glitches in around 20 hertz. Then only we can see these glitches. And then we noticed they have this particular oscillatory nature. If you look very closely in this diagram, there are certain times when these glitches are appearing like this, but there are also certain times when they don't appear. And this oscillatory nature is not a signature of the microseismic ground motion, because when the low frequency ground motion increases, it stays high for a very long time. We don't see them going up and down in this short time scale. But we noticed that the very high frequency ground motion, which is in between 10 to 30 hertz at the corner station, has this kind of oscillatory nature. And this plot shows that glitch rate of these glitches around 20 hertz aligns very closely with this ground motion. This type of ground motion can be created by some machineries which is running on around the corner station. And we saw this perfect alignment in the glitch rate with this type of ground motion. And for the source, this is an optical layout of the detector, and we suspect is this chamber here. This is where the laser is coming from. Then we have these vacuum chambers, and this is the beam splitter, and these are the two arms. And we suspected this particular vacuum chamber here, which is just next to the pre-stabilized laser system. And from measurements we knew that this chamber couples pretty strongly with the DARM. Here is a plot which shows the strong coupling. The black trace here shows the DARM background, and the red trace shows the noise projected from this vacuum chamber ham1. And as you can see, in between this 15 to 20 hertz, the noise coupling is very strong with DARM. So we suspected this chamber, and this was the only vacuum chamber in the corner station which did not have an additional seismic isolation system. During the last vent in summer, they have installed a seismic isolation platform in this chamber, which provides a better seismic isolation for the optic stable that is inside this vacuum chamber. And after doing this, and we have after installing the ISI, we have seen a significant reduction in the glitch rate of these 20 hertz glitches also. Here in gray, I am plotting the glitch rate per minute, and the blue trace again here shows the ground motion. And as you can see, the previous correlation that we saw in the last plot is not here anymore. And this is the projected noise from that chamber now, because this has an additional seismic isolation now. The projected noise from this chamber is much below the DARM background. So here are the conclusions. For the high SNR glitches, we have modeled the noise in two different ways, assuming two different scatter paths. One is scattering happening between the test mass and some structure like the baffles, which is hanging in front of it. And the second scatter path that we assumed was scattering happening between the test mass and the chamber wall. Then we did the correlation analysis, and that revealed that the microseismic ground motion at the corner station along the X-arm is the one which is most correlated with the noise. And installing cage baffles has helped to reduce the rate of these glitches quite a lot. And for the low SNR glitches, we knew that there was some noise coupling going on through the ham1 vacuum chamber at the corner station. And after installing a seismic isolation platform in that vacuum chamber, this noise has gone now. And that's all I have. Thank you for listening. If you have any questions, please feel free to ask now.
Thank you. Thank you, Debasmita, and thank you, Gabriela. And now we have time for questions and for discussion. So you can raise your hand or unmute yourself. I can start with a question while I was wondering, I'm not familiar with this, so it might be a really naive question, but Debasmita, I was wondering, you are seeing these scatter arches. Is there some simple understanding of the shape, why they have this shape as arches? Why it rises and lowers in a symmetric way?
Yeah, so let me go back to the slide. So here this has this sine of sine function. This is a sine function, and in the phase function also we have another sine. That is what gives this archy shape to this noise, because we take an absolute of this sine value, especially when we take the Fourier transform. This is basically an absolute of sine. You can imagine it as that.
I see, that is helpful. Okay, and it's depending on the velocity. Do I understand correctly? Good.
Yes.
Okay.
The phase is a velocity. That's
I see.
how she
I
was
see.
modeling it.
I see. Okay, thank you. That's really helpful.
Yeah.
I don't see hands up. Please go ahead. Yes, Thomas, go ahead.
Yeah, so thank you both for your talks. That was very interesting. So there are lots of interesting things here. One thing that made me perk up is something that Gabriela mentioned, and that is this, I think the signal S251112. And so I think you suggested if that is, I don't want to put words into your mouth, but if it's real, then it might be a very low mass binary. So anything you could tell me about that, I'd be very curious about.
Well, the information we have is that it was found by a code that looks for, and we have several of these, and several codes have found consistent results of a binary system with masses below one solar mass. But the false alarm rate is high,
Right.
at least for
Right.
our taste.
Yes.
We haven't looked at false alarm rates for these low mass signals in a lot of detail. The search for subsolid mass is relatively new.
Yeah. Yeah. Okay.
But it's something nice to see that we can
Very
still see
interesting.
new things.
Thank you.
David, go ahead.
This isn't my specialty either, but I was immediately struck with the idea that have you considered looking at the correlations between the microseismic noise at LVK in order to do any geophysical mapping of the Earth?
Now, Debasmita, if you want to answer that, if not, I can.
This microseismic motion arises particularly because of these ocean waves hitting the seafloor, and they rise during the winter, because in winter we have a lot of winter storms, and whenever the hurricanes affect us, then also this microseismic ground motion goes high.
But about using these for geophysical studies, our interferometer, even though it's very, very sensitive, it's sensitive to a lot of different noise sources. So all the noise sources are mixed up, and we can correlate them, like the Debasmita study has done, with the seismometer at the base or the sensor motions on the chambers. They are not measuring the pure motion of the Earth. They're measuring the motion of whatever the vacuum chamber is sitting on, which is on these big pillars. And so geophysically, these signals are not as interesting. If we wanted to use that, we use the seismometers, not the interferometer.
Thank you.
More questions or comments?
Let me mention while people think about other questions. I see that there are some people who have been around for a while. They are my generation or even before my generation. And I think that we are victims of our own success here, because the more sensitive the interferometer is, the more sensitive we are to these sources of noise that may have been considered negligibly before. So I think this is going to be a game of whack-a-mole. You know, with this, what we suspect now from the recent studies proving is that some of these noise sources might be the same buffers that were there to avoid the scattering noise. And those buffers themselves are producing some of that noise. So this is important to understand, not just for future runs, but for future detectors, that we can measure this and predict it better.
Thank you. Okay, give one more moment.
Know that this was a very different topic than other ones, but I hope you all still enjoy learning about the challenges that there still are about making the detectors more and more sensitive.
Yeah, in the same line as no, the physics target is gravitational waves, but in the meanwhile, we're learning about the detector. Do you have a comment also on all the physics that we are learning by looking for noise sources?
Well, it's not new physics, right? I mean, we are using Newton's equations of motions and Fourier transforms. And so it's not really new physics, but you have to put everything together. You have to see how the rod moves, how that would make a buffer move with respect to a mass. You have to model how that is going to appear in the parameter. So there is a lot of putting physics together.
Mhm.
Just something I like. I think Debasmita does too. I'll let her say that.
Yes, yes, of course.
Okay, if there are no more comments, I would like to thank both of you again. These were two fantastic talks, and it was a great opportunity to hear about these updates. Thank you again.
Thank you.
Thank you all. Thank you for the
Thank you.
invitation again.
Thank you.
Bye.
All right.
Bye.